Hi, in this video I'm going to show how to set up the MC-CT position axis function block from the Control Techniques CT-NC axis interface library. Once the axis is configured, I'll demonstrate how the main features of this interface work. So in terms of the hardware and connections that we've got a laptop. The laptop's been loaded with Control Techniques Connect software. It's also been loaded with Beckhoff TwinCAT XAE shell. There's an Ethernet connection through to our Beckhoff hardware, which in this case is an IPC from Beckhoff, but it could easily be a controller or PLC. The steps would be identical. One of the ports has been configured for EtherCAT comms, and there's a physical connection from that port through to an SI EtherCAT, which is plugged into a Unidrive M700, making this an EtherCAT axis. Now, if you've got one of our dedicated servo products, such as Digitax HD M753, this interface is built into the product. But what you'll find is that the steps you'll see in this video would be identical. So before we get into the demonstration, I just want to point out that all of the steps that you'll see in the video are covered in detail by this manual, which is linked in the description along with the Control Techniques NC Axis Interface library. It's free to download for anybody, and it'd be useful to you if you just don't want to take notes whilst the video is in progress, or if you simply prefer learning step by step from a guide. So, first thing that we're going to do is I'm going to set up a new project. So here we go. I'm going to call this MC-CT position axis. Space there. I'm going to copy this because I'm going to use this name again in a second. I'm going to click OK. And there we go. Our project has been generated. So I'm just going to do a little bit of housekeeping for this particular project. Just get rid of all the things that I don't want to be there. And there we go. I'm going to tell it about my target. And now I'm going to scan for devices. So my PLC's activated, so I'm just going to go offline. There we go. Right. Now scan. So there we go. It's found the EtherCAT interface on the IPC. I'm going to scan for boxes where it should find the drive. Few moments. There you go. It's found the Unidrive M700, and I'm going to say OK to adding an NC axis because the MC-CT position axis function block is built on the NC axis PLC open implementation. So I'm going to say OK to that. I'll activate the free run. There we go. So at this point, the way that the documentation would go is it would tell you to activate the configuration, go online, and then begin to use the Control Techniques Connect software in order to configure the axis and set the speed loop tuning. However, to save time in this video, I've done that ahead of time, so I'm not going to do that step. I'm going to carry on with all of the remaining steps that are required in order to configure the axis. So let's go about doing that. So the next thing that we want to do is we want to add a place for our PLC code to go. So I'm going to do that. I'm going to go and reuse the name that I copied earlier and add. Let's give that a second. There we go. So here is all of our main project stuff. You can see that our access pool has got an axis in. The comms were automatically connected between this and the axis implementation. Before I go too much further, I'm going to go and set the task time to something sensible. 10 milliseconds is a bit on the slow side, so I'm going to go and speed that up, get it to 1 millisecond, which is a good average. There we go. So I think that's everything. So the next thing that we want to do is we want to go and add all the libraries in that we need to set this axis going. So I'm going to double click on references, which is where the libraries are referenced. And I'm going to begin adding in the libraries. So we need to go to Add Library, Motion, PTP, and for this particular axis we need all three of these libraries. You can't add them as a block, you've got to add them individually, so I'm just going to go and do that. And there we go. Next thing, because the position interface also uses STO reads and writes, we need the TC2 EtherCAT library to facilitate those. And last of all, we need the CT NC Axis interface library. So I've already got it installed in my machine, but I'll quickly show how to get it in. So you go PLC, library repository, install, and then use the file browser to hunt to where you've put the library. Once it's been installed, you'll end up with this control techniques category. But I don't need to do that because I've already got the library. So I'm going to go control techniques, applications, and CT NC Axis interface library. And there we go. So that's everything that we need to do to begin writing code. So let's go and do that. So I'm going to expand POUs and open the main program. So first thing, like any NC Axis project, you have to put in an instance of Axis Ref. So I'm going to do that now. So Axis1 of type Axis Ref. There we go. Next thing that we want to do is we want to add in our position interface. So I'll call it Axis1 position, and it is of type MCCT position axis. There we go. Okay, so that's all the declaration done. Next thing that we want to do is I want to add in a place to show the function block in LD. Now the reason I'm showing it in LD is simply because it's much easier to visualize what's going on with the block and to have that kind of hello world playing with the inputs and outputs type moment. So the way I'm going to choose to do that is I'm going to add an action. I'm going to call that action motion. There we go. I'm going to go back to main and then I'm going to call that action motion. So there we go. So now what's happened when main runs, it will actually just execute whatever code is inside action. So let's go back to action, and now I'm going to drop our block in. Get rid of that input, get rid of those, and then I can just enter in the name. So it was Axis1 position, and there's our interface. Last thing that we've got to do is just connect the axis to it, which is Axis1. That's the name given to the Axis Ref. And there we go. So that's basically everything you need to do from a programming point of view for the purposes of this demonstration. The rest is just sort of configuration of the axis, which you'd have to do with any NC axis anyway. So let's do that. So I'm going to build. There we go. No errors. It's important to make sure that you build with no errors, because otherwise the axis ref that you declared here won't appear in the list for connection to this axis. So I'm going to expand the axis and I'm going to go settings, and you can see our, if I scroll this down, our comms IO name is drive 1, and you can see drive 1 Unidrive M700 has already been connected to this axis, but what we do have to do is link it to the instance of axis ref. That's what this button does for us. So you can see we've got main.axis1, that's our axis. So there we go. So next thing that I'm going to do is I'm going to go and configure our scaling. The scaling in a TwinCAT NC axis is done in the encoder parameters. So you select the parameter tab and then set up the numerator and denominator. So the numerator is a number of units. The denominator is a number of encoder counts, and by far the easiest way to set this up is simply to use the default resolution of 65536, and then I'm going to use a resolution of 1000 units per rev. So we know encoder counts per rev and we know units per rev, and I'll just set up the modulo to be 1000 as well. Okay, so that's everything that we need to do in terms of scaling. Now we need to just do the rest of the axis configuration, which is done on the parameter tab. So I need to set up our maximum velocities, and I'm not going to go into the calculation in this video to speed it up a little bit, but I've calculated that 3000 RPM is 50,000 units per second. And my axis is a 3000 RPM maximum reference axis. And then I'm going to take the maximum acceleration limit and put it out of the way. So I'm going to go 1e plus 20, which is a shorthand way of saying 1 plus 20 zeros. Put that in and do the same there. So those acceleration limits won't cause us problems when we're messing about with the inputs and outputs. Last of all, I'm going to go and set the jerk also to that number for a different reason. It's just so that if you put in 0 as your jerk, you'll actually end up with a linear profile, because you'll reach your maximum acceleration within one sample. So we go, that's that. Last of all, the monitoring. I always turn this off to begin with. You can come back and set this later if you like, but normally the default settings just cause your axis to stop implicitly, and then you'll spend half an hour trying to work out why that is. So it's best to just head it off at the pass and just say turn all of these to false. Okay, so that's the axis configuration done. I'm just going to load that into the target. Let's give it a moment. There we go, I think that's working now. Yeah, you can see all of our axis configuration stuff is in our online value, and you can see the green background rotating cog icon is working. So that's telling us that we're ready to go. So I'm just going to log in, and there we go. So what we can see from the off is that we've got some metrics up here that tell us about the state of the drive. So we can see, is the drive on, is it healthy, is it enabled? So if I toggle my enable input, I can see basically at a glance whether we've got all of these properties, so that programmatically we can tell whether it's worth trying to run the axis or not. Now, whilst we're on that subject, you can see that for this particular axis there are several categories of input and output. So I'm just going to run through those. So anything that starts with the letters CMD, CMD is short for command. Those are where we're actively telling the axis to do something. All of the inputs that start with CFG, which is short for configure, these are for setting up the properties of something. So for example, if we were using command jog forward or command jog reverse, we would have configure jog speed, configure jog acceleration, etc. And that follows throughout all of these inputs. Here it will be, if you're doing something with home, you'll go to the relevant configure home something properties. So lastly, you've got outputs that are all of type STS, and you'll see that some of them are Boolean because they're talking about whether a software travel limit is okay or whether a hardware limit is okay. And you've got other ones that are numerical or text-based. So for example, if the driver's tripped on a particular trip, you can normally you can kind of read out what that particular trip value is, or you can read back position following error or speed up following error, something like that. So you can see everything has been laid out in reasonable groups, and as you'll see now, it provides pretty powerful functionality for something that really doesn't take that long to introduce. So let's get going. So I'm going to choose to command the drive to go on. And there we go. We can see that status drive on is on, and we can now see if I go online that our axis is in run. Okay, so that means it's ready to accept a motion reference, which is where we want to be. So just as a demonstration, I'm going to cause the axis to, I'll just put the video on and I'll cause it to jog. So it's a little bit of a delay in the video feed, but there we go. So we're jogging, and we can invert these. Cause it to jog backwards. There we go. What we can also do is, as part of a controlled stopping mechanism that could be used as part of a scheme for an emergency stop, motion stop. So you have to forgive the delay for the video feed, but you can see this rapidly brings it to a stop using the motion stop decel rate and jerk. And you'll find that this is an overriding reference, so it doesn't matter which one of these other kind of motion references that you've got commanded, motion stop will take over. So in order to get the axis to go again, you have to release the motion stop, and then you can command motion again. There we go. That's the axis working again. Next, you've got the homing reference. So the idea of the homing reference is you're just saying to the axis, you've gone to like a position that that could be indicated by a sensor, or it could be indicated by a marker pulse from your feedback device, and we want to reset the position to a known value. Could be 0, could be something non-zero. But you can see here we've got status drive actual position. It says 1.8705, and then if I trigger the home, the default homing mechanism is for home where you are with a position of 0, and now you can see that our actual position has been reset to 0. Okay, so I'm not going to go into all of the homing modes because there's a lot of functionality there. You know, you can home to high precision input, you can home to touch probe input, you can home to a hard stop. There's all sorts of different homing mechanisms in there, all configurable using this selection list. So at the moment we've got home at current position selected, but there's a lot of different ones in here, like home to freeze, which is like a high precision input using MC touch probe under the hood. Okay, so you managed to jog your axis, you managed to cause it to stop. We've also got resetting here. So axis reset, what this does is it resets the PLC open state machine that's used by the NC axis, but it also resets the drive. So for example, if I come in and I use menu 10 and I put a number in here, so I say 26, this will cause the drive to trip on IO overload. You can see it here. But if I come back in, you should see IO overload. So, you know, we read out the trip for you, and what you can do then is you can go axis reset. So I take that off. You can see that the drive is now OK. OK just basically means it's not tripped. And if I double check it, we can see that the axis is in run. So it's quite useful. Not only does it reset the PLC open stuff, but it also resets the drive at the same time. So if you need to do a reset, it's one command to reset. Next, we've got the positioning reference, which is kind of, let's say, the main active reference for this particular interface. So if we come down here, we've got a lot of different things here. So I'm going to go and set my position target to, I don't know, 10 revolutions. So we've got 1,000 units per rev, and I've put in 10,000, so that's 10 revs. I'll leave the speed, and what I'll probably do, you've got a range of different types of motion. So you've got absolute, relative, automatically indexing, automatically reciprocating. So these two are kind of references that you might use for tuning. So auto reciprocate basically says move forward by this amount of distance and move back by the same amount of distance, and it just repeats and repeats and repeats. So you could use that in order to tune. And then finally, a modulo reference. So if you're doing something that's a rotary application like a carousel, you can get it to turn within one set of, you know, modulo or rotary boundaries. So 0 to 999, for example. So for me, I'm just going to pick relative. I think that's probably enough to demonstrate this. And then I'm going to select the position reference. So in a minute, the video will catch up. There you go. So that's moving on, doing the 10 revolutions, and then it will come to a stop. And there you go. We can see that position has become complete. Position is active. You can also see that even though the homing reference isn't on, that a homing has been completed. So there's lots of nice status information over here. Lastly, you've got, in terms of commands anyway, you've got the ability to enable and disable software travel limits, and you've got the ability to configure the software travel limit positions here. You've also got the ability to define the deceleration rate that gets used if these limit gets hit. So that's quite useful. And you've also got freeze flag resetting. So freezing is a Control Techniques terminology, but essentially freezing is analogous with MC touch probe, which is a DS402 feature, which is the underpinning comms protocol that's used by EtherCAT. We've also got the ability to reset the error reporting. So the error reporting that you've got is because inside this function block we use several function blocks from the PLC Open library from Beckhoff. Okay, so there's things in there like MC power, MC move velocity, etc. And all of those have their own error output. So what we've done is we've made it so that all of those errors get put together and are reported via this error reporting mechanism. So you can tell whether one of the blocks has got an error, you can tell the text for that particular error, you can tell which function block has the error, whereabouts in the software that error is, and the particular number of that block in the system, so that if you wanted to, you could focus on that particular error. You've also got the ability to tell, just in text, to see what the state of the PLC open state machine is. So, another feature that you've got that doesn't necessarily have a command input, it's more of a configuration thing, is you've got the ability from this interface to configure stopping on the following error. So what this will do for you, instead of the system that's built into the NC axis, which will just immediately disable the system in the event of an error, what this will actually do instead is bring it to a stop using a deceleration rate that you've chosen, and then disable the axis at the end. That way, if you've got an axis that's doing some hoisting, for example, and you've got a mechanical brake, the axis will be stopped by the time that the brake becomes engaged, and therefore you're not going to be damaging your mechanics. There's a little bit of a time delay in there, so you can choose how long the following error has to be there in order to detect it. So if, for example, your particular setup has got following error that peaks a little bit during acceleration, but it's normal for its operation, you can filter out responding to that using this time. You can also choose whether you want to respond to positional following error on its own, speed following error on its own, or position and speed following error using the limits, so for speed following error and position following error. Okay, one last thing that I think I'm going to point out is that we've done something for these axes in order to allow you to be able to identify them easy if you've got a large network of drives. So by default, the axis name here is set to 1001. Okay, so for those of you that are, I'm just going to close that. For those of you that are familiar with the axis node numbering system, you'll see that here is the EtherCAT address, and we take that information from the axis itself and then push it in by default as the axis name. Okay, so we're online now, and what you can see if I scroll up, this 1001 node number has been pushed into the drive name. So we can change that if we like. It doesn't have to be the node number. You can put whatever name you like, up to 16 characters. So let's have a little go with that. So single quotes, and I'll go Nidec drive. Not very original, but you'll see the point. Push that in, and now our drive is called Nidec drive, and you can cause this name or these values to be displayed on the drive by configuring 1179, for example, as a status mode parameter if you've got the old keypad display, or you can use the SI keypad plus setup menu for the status parameters, of which you've got 10, and you could make this one of those. That way you've got a way to identify things that you see on the drive's display with what you see in TwinCAT, and also with what you see inside a Connect. So it's actually quite a nice feature if you've got quite a large system and you're struggling to identify which node is which. So coming back to this, I'll quickly run over all of the outputs. So we've covered these ones. So here we've got a category of outputs that's just telling us with a Boolean flag, are we at 0 speed, or are we at the speed that's been commanded? Are we at the home position? Then we've got the active outputs. This is jog active, is home complete, position active, etc. We've then got software limit indication by a single Boolean, so we can tell whether positive, negative software limit, positive, negative hardware limit. And when we're talking about hardware limits, what we're really talking about, if I come back into here and go limits, when you configured the axis, if you configured a hardware input to the forward and reverse software limit, that's what that really means. It's talking about those. We have the ability to see whether we've captured any freeze information. So this is information from triggering a touch probe effectively inside, and then this is the position that it's managed to sample at the point that this was triggered. Okay, we can tell whether the axis has stopped because the following error is too high. This bit will become set if that has happened. This bit will become set if the comms has failed during operation, so that it will basically stay there and tell you that it's failed, and that's why. So you've got a clue. This is the PLC open function block error handling mechanism. drive trip and alarm handling mechanism, drive load, and then these last ones are actual position, profile position, and following error. Okay, so the following error is the difference between the actual position and the profile position. So that's the basics of the features. It's not too complicated, but there's certainly a lot of functionality there that if you had to coordinate all of these different sets of functionalities, you would be coding for quite a long time. It's not just a case of slapping one or two MC type function blocks in there. There's quite a lot of work. But if you're working with the axis and you want to sort of troubleshoot, we've left all of these blocks open. So if you double click on the block, if you're in the LD editor, you can see all of the functionality is in these different categories, and they're all reasonably sensibly named. So you've got things that are inputs, power, limits, freezing, which is kind of the same as touch probe, jogging, homing, positioning, stopping, current limits, etc. Okay, everything pretty clearly labeled for what its purpose is. And if I go into one of these, so you right click and then go to instance, here is all of the code involved with organizing that to happen, and here is the instance of MC jog, okay, and its control logic and where its references come from. So you can see we left everything kind of open basically, so that it's not a black box. You can kind of go in there. You can even copy this and rebrand it yourselves if you want to make your own function blocks to save yourselves time. So there we go. I think that's covered everything for the MCCT position axis function block. I hope you found this useful. Thanks for watching.